So now we want to talk about the acceleration of an object due to gravity. So anytime we have an object falling or in free fall near the surface of the Earth, right, so anything falling down, it's going to have an acceleration of negative 9.8 meters per second squared. We usually use the variable g when we're talking about a falling object, so g would be 9.8 meters per second squared. We usually define g as being positive 9.8 meters per second squared, but you have to keep in mind the situation, right? If we're falling and your reference frame is that down is negative, you're going to plug it in as a negative 9.8 meters per second squared because we're moving towards that direction. If we look at our kinematic equations, right, let's just take, for example, x equals x naught plus v naught t plus 1/2 at squared was our equation. Instead, we might write it as for a falling object, x naught plus v naught t plus 1/2 gt squared, so that we're plugging in that 9.8 meters per second squared. And again, if our reference frame is that down is the negative direction, when you actually plug in a number here, most likely you're going to plug in negative 9.8 meters per second squared. So you have to keep in mind that directionality of it. Also keep in mind that if we're ignoring air resistance, like we're going to do for all of these problems, this constant acceleration of 9.8 meters per second squared downward is going to be true for all objects. All objects near the surface of the Earth are going to fall at the exact same rate. Okay, so it doesn't matter if we're talking about a piece of paper or a book in the problem, it's going to be the same if we're ignoring air resistance. Being able to analyze graphs of motion is a skill that's incredibly important in this class, and it's something you need to get really good at. So real briefly, we just want to look at what some of these graphs might look at. And we'll look at an object that maybe we throw up in the air and comes back down. So we're going to make 3 graphs. We're going to have our position versus time graph. In this case, we might actually choose to use the variable y, since we're talking about the vertical direction. We're going to have our velocity versus time graph, and our acceleration versus time graph. Okay. We're going to start with our acceleration versus time graph because that's going to be the easiest one. Our acceleration is be that constant, negative 9.8 meters per second squared, and it's going to be that the entire time. Right? As it's flying through the air, if we're ignoring air resistance, the only thing acting on that object is gravity, so the acceleration it experiences is just gravity that entire time. If we think about velocity as an object goes up in the air, as it goes up in the air, it's going to start quickly and then slow down until it reaches the very top. When it reaches the top, its velocity is actually 0 for a very brief moment in time, and then it's going to continue and it's going to speed up, but it's going to speed up in the negative direction. Okay? So it's going to get a larger and larger negative velocity. So our graph for velocity versus time would be like this. If we look at the slope of that graph, right, slope would be kind of rise over run is the way we usually think of it. Well, our rise in this case is our change in velocity, and our run is our change in time. Well, change in velocity over time is equal to acceleration. And if we're talking about an object falling through the air, our acceleration is negative 9.8 meters per second squared. So the slope of this graph should be negative 9.8 meters per second squared. So the slope of a velocity versus time graph is our acceleration. For position versus time, right, we get further and further away, but at a slower rate. So we end up with something kind of like this. And then at that point where we turn around, we get closer and closer to where we started, but at a faster and faster rate now since we're speeding up. So our position versus time graph would look something like that, which should make sense to us because if we remember our equation, if we write it in terms of y equals y naught plus v naught t plus, in this case, 1/2 gt squared. Well, that's a quadratic equation, so our graph should reflect that, and it should look like a quadratic function, which it absolutely does in this case. And kind of an interesting feature of this, if we were to draw a tangent line, so a line that is just touching a single point, and find the slope of that tangent line, it would give us the velocity at that exact moment in time, which makes sense if we look at the very top of our motion. Here's a good way to think of it. Our tangent line would look something like that. Well, what's the slope of that line? If it's just a horizontal line, then our slope is 0. So our velocity, not 6, but 0. So 0 would be our slope, and 0 is also, remember, our velocity at the very top of our motion, right when it turns around. So all three of these graphs match up, and they describe that motion well. So you're going to need to be able to think about a graph of an object and describe its motion, or vice versa, from a description of motion, be able to describe the graph, position versus time, velocity versus time, acceleration versus time graph that object would make.